Good afternoon and welcome to our Speaker Series event. My name is Vakhtang Putkaradze and I'm the Vice President, Transformation, Science and Technology for ATCO, and I will be your moderator today. I would like to start by introducing George Constantinescu, Senior VP and Chief Transformation Officer at ATCO, who has some welcoming remarks and will introduce our speaker. George leads ATCO's transformation team and SpaceLab initiative. Building our internal expertise is one of the top priorities of the transformation team, and therefore an important part of this effort is ATCO Speaker Series, which gives us an opportunity to connect with top experts in the field like Professor Doering. Moreover, George has extensive experience in utilities, so the future of utilities, and in particular, their safe, efficient operation is a topic near and dear to him. George, thank you so much for joining us today, and I'll turn things over to you.
Thank you, Vakhtang, for that very kind introduction. I would like to begin by, first of all, asking if everybody can hear me. Thumbs up? Perfect. I'd like to begin by conveying Nancy Southern's regrets that she can't join us for this session today. She was very much looking forward to it. Unfortunately, she got called away in an urgent business matter, but she's certainly here with us in spirit, and she welcomes you all to this what's going to be a very, very interesting discussion. And I'm very pleased on my own behalf to welcome you all to our third ATCO Speaker Series. I'd like to begin by acknowledging the traditional owners of the land on which we are, wherever you are located. I would also like to pay my respects to elders, past and present, in the communities and regions where we operate. We have a number of my ATCO colleagues on the call, as well as others from the academic, community, and business sectors. So a very warm welcome to all those joining us today. I would like to do a little bit of self-promotional congratulations by commending my team for convening these speaker series sessions. They represent a chance for us to share and discuss knowledge and insights from thought leaders of global renown. Our aim is to provide ATCO's people and our network of peers, partners, and friends with information on promising developments, trends, and leadership in relevant fields. I think it's very exciting that on April 7th, we will be hearing from Professor Jonathan Schaefer from the University of Alberta about what artificial intelligence is and what it is not. And on April 30th, Professor Valerio Lucadini from the University of Reading will talk about understanding extreme weather events. Now to today's topic. I'm thrilled that today's session will focus on how to predict difficult to find solutions to complex problems. This is especially important for the operation of ATCO's highly complex electric and gas grids. Our electricity division delivers reliable power over about 85,000 kilometers of transmission and distribution lines. We safely deliver this power to nearly 225,000 customers in 45 communities, and our service covers nearly 2/3 of Alberta. Our gas distribution network in Alberta reaches 1.1 million customers in over 300 communities. In Australia, we deliver natural gas to 750,000 Western Australian homes through 14,000 kilometers of pipeline. With such an extensive network, new challenges in operation are constant. In addition to familiar challenges to grid operations, like inclement weather and construction, new opportunities like distributed energy resources make grid operation less predictable. Proliferation of electric vehicles in residential neighborhoods can also put a unique strain on the local grid, which was not designed to operate with electric vehicles in mind. Challenges like these appear constantly in our operations, and we are committed to successfully solving all these problems and be future ready in our utilities business. That is why my engineering colleagues on the call will welcome Professor Doering's lecture. This lecture will be the first one in the series of lectures that relate to the enhanced understandings of our transmission and distribution networks and excellence in operations. So that gives you an insight into why ATCO is very interested in hearing more about research and learning that Dr. Charles Doering will share with us. Please stay with us for what I hope will be a lively discussion after Professor Doering's lecture, starting around 12:45 p.m. And it is now my pleasure to welcome and introduce our guest speaker. Charles Doering is the Nicholas D. Kazarinov Collegiate Professor of Complex Systems, Mathematics, and Physics, and is the director of the Center for the Study of Complex Systems at the University of Michigan. His research is focused on the analysis of mathematical problems and models with the aim of extracting reliable, rigorous, and useful predictions. These models range from stochastic, dynamical systems arising in biology, chemistry, and physics, to systems of nonlinear partial differential equations, such as those that describe turbulent fluid flows. And I still have some disturbing and vivid memories of that series of courses from my very ancient academic background. Professor Doering received a bachelor's degree in mathematics and physics from Antioch College, a master's in physics from the University of Cincinnati, and a doctorate in mathematical physics from the University of Texas at Austin. He held positions at Clarkson University and was the director for the Center of Nonlinear Studies at the Los Alamos National Laboratory prior to joining the Michigan faculty in 1996. Professor Doering is a fellow of the American Physical Society and of the Society of Industrial and Applied Mathematics. And among other recognitions, he has received the NSF Presidential Young Investigator Award, the University of Michigan's College of Literature, Science, and the Arts Excellence in Education Award, a Fulbright Scholarship, and a Humboldt Research Award. He was named a Simons Fellow in Theoretical Physics in 2014, a Guggenheim Fellow in Applied Mathematics in 2016, and the Simons Fellow in Mathematics in 2021. Professor Doering is also a big supporter of University of Michigan football, and his passionate support of U of M was even mentioned in the New York Times. Professor Doering, thank you so much for joining us. With that, I will turn it back to Vakhtang to explain the format of today's session. Vakhtang?
Thank you, George, for a great introduction to the speaker and this lecture. Again, welcome everybody who has joined us. This is, as George mentioned, the third lecture in ATCO Speaker Series. Before we go underway with today's lecture, I would like to remind you that this session is a one-way video and audio format. You can see and hear the presenters, but they can't see or hear you, which is not the greatest for audience feedback. So that's why we're encouraging you to ask questions. You can do so by using the question icon at the right of your screen. We will open up the question functionality roughly midway through Professor Doering lecture. You can address your questions to him. With that, I would like to pass the microphone to Professor Doering. Great to have you with us. Please go ahead.
Great. Thank you both very much. It's great to be with you virtually. I just want to make sure you can see me. Yes? Somebody say yes? Nod? Okay. And you can see the screen. Yes? Okay. And you can see the blue pointer, which is now freezing. There it is. You see the blue pointer, right? Okay, good. I want to make sure. Okay, so the title of my, actually the technical title of my talk, or the title of the technical talk will be Optimal Bounds and Extremal Trajectories for Time Averages in Nonlinear Dynamical Systems. That's quite a mouthful, but I'm going to be focusing on some technical stuff, but I want to motivate it first. Let's motivate it. And let's see, here's a physical problem, which also might bring back some nightmares for George. Consider a duct, a rectangular duct, and you've got a fluid flowing through it. It could be a gas, it could be a liquid, whatever. And what you're interested in is for a given pressure drop from end to end, how much fluid flows through there. Well, we have equations that will tell us this. These are the Navier-Stokes equations. And all we have to do is get a computer and do some numerical analysis and come up with a scheme and solve these things. Well, that sounds easy to do in principle. And in fact, it was done. It's been done many times. But here's one example of such a flow. This is from work already last decade. But this is a petascale direct numerical simulation of those equations for turbulent channel flow. Now, the picture here is a cross section of the horizontal velocity going down the pipe there, and you see that it's rather complicated. It's turbulent. This is a snapshot of turbulence. The color means denotes the speed, how fast things are going. But another aspect of this is that it's incredibly multi-scale. If we zoom in on this little corner down here, you see that you still have an incredible amount of structure at scales much smaller than the width of the channel. And if you zoom in down here even more, you see you still have incredible amount of structure in the flow there. Now this is, as the title of this paper says, this took 750,000 computer cores to compute, and it took 250 million CPU hours to compute this. So this is a major issue in computational fluid dynamics. But the issue is, we got all this information, put in all this effort, but really all we want to know is the mean flow. I just want to know how, what's the mass per unit time flowing down this pipe. I don't necessarily often want to know all this stuff. Sometimes we just want to know the friction coefficient, one number. All of this computation for one number. And this really summarizes, for complex nonlinear dynamical systems in general like this, it really sums up the problem. In fact, my good friend Sergei Chernyshenko, who's an aeronautical engineering professor at Imperial College, says the problem of turbulence is how to figure out how to buy a glass of milk without buying all the cows. We don't really want necessarily all that detail. Now, this is a problem. This is not just fluid dynamics, which I'm particularly interested in, but let's think about systems biology. There, in systems biology, we're interested in what are how do the protons and DNA and RNA interact to make things work. Well, here's a specific example. This is from a paper about modeling a regulatory mechanism, right? And you start off with some idea of metabolic pathways. Various things. I'm not even sure what these symbols mean, but I'm sure you guys all do. I know what DNA is down there at the bottom there. But then this gets transformed into a biochemical reaction network. Now I can more clearly start to understand what's happening. But then at the final level, we turn it into a system, these things into systems of nonlinear ordinary differential equations. For that particular model, this is 65 coupled nonlinear equations there. And then you put it on the computer and you have to pick parameter values for the, I don't know how many parameters there are in here, many dozens of parameters, and you predict things. And you get all this detail. But really, what we want to know is the average production rate. We just want to know how much, at what rate is the DNA producing a certain kind of protein that's doing a certain function at the end there. Now, something you all don't need much motivation for is, I put up this picture and you know what you're thinking. I mean, I know what you're thinking, that's something relevant. Of course, in this situation with things like power grids, it can be distilled down to the basic networks there. And of course, to study various aspects of it, you can model it, putting at each node of the network, you put various differential equations involving various things. Now, this might be the whole system, this whole large system of dynamical equations might be worth simulating if, for example, you're interested in cascades, which are phenomena which I think We don't want to see too much if it's a cascade of failures, but sometimes we just want to know average production rates or average transmission rates on these things. But all in all, that is meant to motivate why we might be just interested in going straight for averages, information about averages, without getting all the detail on the side. We want the glass of milk, but we don't want to buy all the cows. So what I'm going to do is describe a mathematical theory that's emerged recently, just in recent decades, for doing this, and I'll give some examples and so on. And I'm going to warn you, this will get a little bit mathy, but it's not too mathy. And if I get a little bit abstract, just hold your breath, fasten your seatbelt. It'll be quick and I hope painless. We'll get through it for maybe the few experts out there. So the outline of the talk is the content of this paper that was published a couple of years ago in Physics Letters A with my collaborators Ian Tabasco and David Gillespie. Ian was a postdoc with me, as was David at the time, and he is now an assistant professor in the Department of Mathematics at the University of Illinois in Chicago. And David Gillespie is now an assistant professor at the University of Victoria in up there. He's a Canadian now, although he's from New York. And I'm Charlie. Yeah. Okay. So let's get into it. The mathematical problem. We have some differential equations. We have these x of t variables, which are d-dimensional variables. So this is d differential equations, nonlinear, and so on. F is the vector field that defines the evolution here. And as I've just motivated, sometimes for these complex systems with complicated solutions, we're often interested in statistics or long-time averages of key quantities. Now, averages for solutions of differential equations can often depend upon initial conditions. So different initial conditions might produce different averages. And so we're going to even back off a little more and say, well, let's focus on the largest possible or perhaps the smallest possible average amongst all solutions or all trajectories there. And see if we can focus on these kind of quantities basically without buying all the cows there. Okay, so if we have a certain quantity of interest that I'll call phi, that's the function of the dynamical variables whose long time average we're interested in, then I'm going to define the long time average of that quantity by an overbar. And the overbar, of course, generally depends upon the initial condition where we start. And so I live in a math department, at least partly, so I can't assume limits exist, but lim soups always do. But this is the long time average. Okay. Now, long time averages for mathematical models, this could diverge. This could be infinity. So we're going to focus specifically on bounded dynamical systems. So in our phase space, which is RD, right, d-dimensional Euclidean space, but we're going to focus on systems where there's a ball, an invariant ball, which is a closed bounded region, so that trajectories that begin in that ball remain there, or it could be that if for what are called dissipative systems, solutions all enter the ball and stay in there afterwards. There. So that's what we're interested in. So we're interested in, if we're interested in the largest long time average, we could also do the minimum. It's just we reverse max and min all over the place, but we'll focus on max here. I'm going to define the maximum possible long time average of phi as phi bar star. And that's the max over all the initial conditions that start in that ball of the time average of that quantity there. So the fundamental questions that we're going to ask here mathematically, we're going to seek is what is the value of phi bar star? And I don't want to get it by solving the differential equations millions of times with millions of different initial conditions and then picking the largest. I don't want to do that. And also, if we can determine what this largest value is, we may be interested in the trajectories or the initial conditions that produce it. Because we may, for example, want to maximize prediction of something, so we'd like to know what solutions might do it and how we might realize them there. Now, here's a simple fact. And here I'm going to do a little calculation here, which is okay. Upper bounds, as it says on time averages, we can get upper estimates or upper bounds on the largest possible time averages, following from the fact that the time derivatives of bounded functions average to zero along trajectories. Okay, that's another mouthful. What does that mean? Well, it means this very simple calculation. Given an initial condition in this ball, and any continuous function v of x, this is you pick any continuous function that's a function on the ball, maps into the real numbers, then the fact of the matter is, if I take the gradient of v, which is a vector field, and dot it into my vector field, which defines the dynamical system, that's a function, that's a real valued function on the ball, and I can take the time average of that. Well, the time average of that, f dot grad v by the chain rule, is just the rate of change with respect to time of v of x, where x is one of the trajectories. This is just the chain rule of calculus. And so I know how to calculate time averages of time derivatives. Well, here's the time average of the time derivative, and the fundamental theorem of calculus tells me that this is nothing other than the fundamental theorem of calculus, that's the value of v at some late time minus its initial value, both of which are bounded real numbers, divided by t, take t goes to infinity, is zero. So what this tells us is that we have an infinite selection of functions which, when we evaluate their time averages along trajectories of the dynamical systems, they give zero. Now, okay, zero. All right, that doesn't sound very interesting, but it is, as you'll see. Now, in particular, for any such v that we have, any nice continuous function on the ball, the time average of the quantity we're interested in, phi, is exactly equal to the time average of phi plus this f dot grad v function, right? So I can add a whole bunch of different things to phi and be guaranteed they'll give the same time average there. All right. Now what use is that? Well, what use is that is that, well, if we want upper bounds on this time average of phi, we can just take upper bound, a pointwise upper bound on the value of phi plus f dot grad v for any v. A time average can't be bigger. A time average of some function can't be bigger than the maximum value of the function. So we get something that looks like a crude upper estimate. For any initial condition, the time average starting from there is less than or equal to the maximum over the ball B of phi plus f dot grad v. Okay. The point is that v is arbitrary here. There. And I just written that up there. This v, I'm going to refer to as an auxiliary function. Now, in the ensuing things, if you know something about dynamical systems and differential equations, this is going to start to smell like a Lyapunov function. But it's different, but it's sort of in the same spirit, where we're going to utilize the freedom that we have to select these to do the best we can. Now, to obtain the best possible bound that we can, upper bound on the largest possible time average, what we want to do, since v is arbitrary, we want to take the infimum, or that we want to minimize the right-hand side of this thing, minimize it over the v's, over the auxiliary functions there. And so that gives us the best upper estimate that we can get by this technique for the largest possible time average of this quantity for our dynamical system. Now, it turns out that this minimization, taking the infimum or minimization over these things, is a convex minimization. And convex minimization is a convex function. The nice thing about minimizing them is we know that there is a unique answer to the question, which is not true if we're trying to minimize over a non-convex function that has many local minima that are distinct. Now, the main result that makes this stuff work is that this optimization, the optimization over auxiliary functions and maximizing over initial conditions for the dynamical system, are what are called dual variational problems. And they're, in fact, what's called strongly dual, which means that this inequality right here is actually an equality. That in order to get the actual answer for the largest possible time average is exactly equal to this infimum over the auxiliary functions, this minimization, convex minimization. Good. Now, this idea emerged late last century, I mean, in the 1990s. In the abstract dynamical systems went under the name ergodic optimization. And those people, those are abstract dynamical systems people, and they proved some theorems, but they never solved any problems. But there's a certain kind of technology that's emerged in this century where we see how we can use this to actually get information out of interesting problems and develop effective numerical methods to extract them there. So what it just says here is, thus arbitrarily sharp bounds on the maximal time average can be obtained using increasingly optimal auxiliary functions. This is great. Moreover, and I'll show you examples of this, the optimal or nearly optimal auxiliary functions, if we can find them, can be used to locate the maximal or the extreme trajectories in phase space. In other words, we can figure out which solutions are doing the best on average. There. Okay. Now this is going to be one slide, 4 lines. This is for the experts in the audience. Why are these dual variational problems? Well, I'm going to tell you why, because the maximum time average of phi, overall initial conditions in the ball, is nothing other than the maximum of the expectation of phi over all invariant measures. I won't tell you what invariant measures are, but if you know, then you know. Now, the thing is, the set of invariant measures is very complicated because that has all the information about the dynamical system. But we can unfold that and make that just a maximization over all probability measures on a ball. Then that's something, we have a domain, we think of all probability measures by introducing an f dot grad v term inside that integral and taking an infimum over this auxiliary function, where v is any C1 function there. And the point being is that if mu is invariant, then this f dot grad v integral d mu is 0. So we didn't add anything. But if mu is not invariant, then there's at least one v for which this is not 0. And then I can choose the SIGN of v and the magnitude of v to make this as negative as I want, and this infimum will be minus infinity. So this infimum is minus infinity if mu is not invariant. It's a finite number if mu is invariant. So that's the way we unfold this. But now we have a max-min problem. And then you check the soft analysis about, this is a saddle point problem. And it turns out you do the functional analysis and make sure that's true. This is the same as the min-max. So I can switch the max and the min, and I'd be sure I get the same answer with no gap. And then this supremum over all measures on the ball is nothing more or less than just the maximum value. You just put a delta function where phi plus f dot grad v is maximum there. And that's exactly the answer. There we go. Done with that. You can exhale now. Okay. So let's see. What about these optimal trajectories? Well, if I have an initial condition and an auxiliary function that are truly optimal, the relationship will be that the time average of the function of interest starting from a trajectory with that initial condition actually is the maximum value over for all points on the ball of this function phi plus f dot grad v there. Okay. Now, and in fact, for the trajectory that starts at such a place, then if I was to follow along a trajectory as a function of time, as I'm to follow f phi plus f dot grad v along there, that is going to not change. It's since the time average is the maximum value, and you can't go above it, then if I'm going to have the time average be that, I have to spend almost all the time at that maximum value. What we're going to think of is this phi plus f dot grad v for an optimal auxiliary function is a mountain range over the ball in RD. It's some real valued function. Think of it as some fitness function or some mountain range there. And the optimal trajectories live at the high altitude points of that mountain range there. And in fact, extremal trajectories, what it says, are a subset of the maximum set of that function. I'm going to do a very simple example now where we put this all together. Okay. Now here is a simple example. This is a one-dimensional ordinary differential equation. That's my dynamical system. So this is in R1. So dx dt is equal to x minus x cubed, and that's my vector field, so to speak, f of x. There. Now this is a very simple differential equation. Oh, I say what's the quantity we're interested in? Well, let me suppose I'm interested in x squared. So and what I want to know, what's the long time average of x squared? So that would be like a variance or second moment of the solution, long time averaged there. Okay, well this dynamical system is very simple, and we know what's happening. Here's our phase space, rd, d equals 1, and the flow on this phase space is very simple. Anything that starts less than -1, any initial condition flows toward -1. Anything that starts to the right of 1 flows toward 1. 1 and -1 are fixed points, stable fixed points. And if I start in between, if I don't start exactly at 0, then I'll flow either to -1 or +1 as the arrows indicate there. So basically it says that for this very simple system, every solution except the one starting at 0 is going to flow to -1 or +1, where x squared is equal to 1. So the long time average, the answer is going to be 1 for the largest long time average. The smallest long time average is 0, because if I start at 0, I stay at 0. But how do we get that out of this thing? Well, this system is simple enough that I can just guess it was an informed guess, but I can guess an optimal auxiliary function. And I claim that v of x, which is just 1/2 x squared, is an optimal auxiliary function. Why is that? Because, well, let's compute phi plus f dot grad v. So phi plus f dot grad v is phi plus f of x times v prime, that's the gradient. And if I put that in there, phi is x squared, the vector field is x minus x cubed, and v prime is just x. Well, when I multiply that out, that's 2x squared minus 4. But then I do a very simple completing the square and see that's 1 minus x squared squared. So this is 1 minus a non-negative polynomial, right there. So I know that the upper limit of this is equal to 1, right, the upper bound. And if I plot that phi plus f dot f v prime, there's my mountain range. And the maximum value of the time average of phi is exactly 1. It's the peak value of this mountain range there. And the optimal trajectories here are fixed points, and they live right at the top of those mountain ranges there. Very simple problem there, but I hope that clarifies it. Now, I will also say that even if we don't have a purely optimal auxiliary function, but we've got a nearly optimal one, and by nearly optimal, and we know nearly optimal ones exist because this is a convex variational problem. I know that I can approximate arbitrarily closely the optimals there. In that case, the difference between the mountaintop, the max of phi plus f dot grad v, and the actual long time average about relevant nearly optimal trajectory is smaller than any epsilon I choose. I can find such a v. And in that case also, of course, we remember that the mountaintop is always bigger than or equal to the largest time average for any v, and the largest time average is, of course, greater than or equal to the time average for any particular v, because this thing is 0 in time average. There. Okay, that means that if we choose some number m bigger than epsilon and consider the set in phase space, that's the set of points in the ball, where the maximum, that's the top of the mountaintop, is within m of these points, so x is x of the points that are just a little bit less than the mountaintop, then we can also prove that the amount of time that an optimal trajectory spends there is a fraction of time is 1 minus epsilon over m. So as we get better and better, have smaller and smaller epsilon, we're assured that our optimal trajectories spend more and more time in these sets. To put that to a picture, suppose I wasn't so smart and didn't know that v of x is 1/2 x squared is truly optimal. And I guessed something else, but it was pretty good. It was nearly optimal. Well, if it's nearly optimal, then the 5 plus the mountain range won't be the optimal mountain range, but it'll be something that has to be a little higher. Its highest peak has to be higher because the highest peak is exactly equal to the answer when I optimize there. But when I have a situation like this, if I then choose an m that's not too big and look at the set of x's that are within m of the maximum, then that will be an interval around 1 here and an interval around 1 here. And in that case, I'll be able to say that for a very large fraction of time, the optimal trajectories will live here and here. Right? So I can get, of course, for this one-dimensional problem, it's may seem kind of trivial, but it's important in practice. Yeah. Okay. All right. Now, how do we, besides these simple examples, how do we really operationally compute these bounds? How do we operationally perform this kind of convex optimization? Yeah. Well, let's consider polynomial systems, polynomial problems. By polynomial problems, I mean, like my little differential equation there, the components of the vector field are polynomials in the dynamical variables, right? And that the function phi I'm interested in is a polynomial, like x squared, right? And I'll show you other examples as we come here. Well, the statement that we have an upper bound u on the largest possible time average, you will agree is equivalent to the statement that u is an upper bound on phi plus f dot grad v. I shouldn't say is equivalent to, is implied by this, because we get the best one by minimizing over v. And that latter statement is exactly equal to saying that u is a number such that u minus phi minus f dot grad v, which are all polynomials I'm considering here, is a positive polynomial. But actually, it turns out that checking whether a polynomial is positive is NP hard. As the degree of the polynomial and the number of variables in the polynomial increases, the checking whether it's actually positive everywhere is it becomes exponentially difficult there. So we note that the thing that we want is implied by the statement that u minus phi minus f dot grad v, which is a polynomial, is a positive polynomial. That's NP hard. That's what I just said. But that's implied by the statement that u minus phi minus f dot grad v can be written as the sum of squares of polynomials. Because, of course, the sum of squares of polynomials is a positive polynomial. There are positive polynomials that can't be written as sums of squares, but by relaxing the problem a bit and requiring that this quantity can be written as the sum of squares of polynomials, I'll refer to those as SOS problems. The neat thing about that is that this optimization problem, optimizing over polynomials of a given degree, such that u minus phi minus f plus minus f dot grad v is the sum of squares of polynomials, and u is as small as possible, that can be performed via what's called semi-definite programming. So semi-definite programming is a certain convex optimization procedure. And this is something, for those of us who live in the dynamical systems world, we're interested in differential equations and partial differential equations and dynamical systems and all these things. Well, one thing I discovered in this business, well, actually, my collaborators and I discovered, there are more people who work on convex optimization problems and more programs and more software and more algorithms than by probably an order of magnitude than there are for solving differential equations. So there's an entire technology, computational technology out there that was just waiting to be brought to bear on these problems from dynamical systems here. Okay, let me do an example, a very specific example that's not one-dimensional. It's still low-dimensional. This is a paper that David Galuskin, who I introduced before, wrote while he was a postdoc with me. It just appeared also in 2018, Journal of Nonlinear Science. And it is using this technology to bound averages for mean moments of the Lorentz equations, the Lorentz systems. Now, what are the Lorentz equations? The Lorentz equations is a three-dimensional dynamical system, x of t, y of z, t, z of t. And these are the differential equations. Sigma, r, and b are parameters of the problem. And where do these things come from? These are very, very famous equations. You've probably heard of them. Well, where do these equations come from? They are a very reduced model of what's called Bénard convection. If you take a fluid, normal fluids, and if you heat them from below and cool them from above, well, most fluids, when they're a little bit warmer, become a little bit less dense. And the cooler fluid would be a little denser. And in the presence of a gravitational field, pointing in the usual down direction here, this would create an unstable stratification. You'd have heavy fluid over light fluid. And we know that likes to turn over. And it starts to convect, and the fluid will start to flow. And in fact, this parameter R exactly is that parameter that indicates how much you're heating it, heating the problem. And the X variable is actually the magnitude of the convection, the speed of the convection roll that ensues once it gets going. And Y and Z have to do with the temperature profile that results in this. This is a very reduced, what's called the Galerkin truncation of the partial differential equation for fluid dynamics. But there it is. This is a very important, historically important model. So let's focus on it and see what this technology does. Consider the standard parameters, which happen to have chaotic solutions. That's where B happens to be 8/3, sigma is 10, which actually corresponds to a fluid that's sort of like airish, atmospheric Prandtl number. That's a characteristic of the fluid. And this R variable, the heating, or the Rayleigh number in this system is 28. It's a specific value of the parameters. Now, there's a lot of interesting solutions to these differential equations here. And in fact, here are, or invariant sets, let's say. These are sets to which the solutions go after long times, after they relax. One very familiar set is that butterfly wing chaotic fractal set, which you may all have seen, that was really, this is very much where Lorentz in 1963 discovered chaos, dynamical chaos in this setting. But there are also other solutions. There are fixed points. There are these fixed points. There's a fixed point at where x, y, and z are all 0, which means the fluid isn't flowing at all. The fluid is just at rest. And then there's these other two fixed points, one here and one here, which are the same as these two fixed points. These are just looking at the three-dimensional space from different directions, which correspond to steady convection, where the rolls are just moving steady. And the chaotic trajectories is where the rolls, they speed up, and then they reverse, and then they go back and forth. And that means basically the wind is blowing one direction, the other direction, and chaos means it's hard to predict which way the wind is going to blow tomorrow, even if you know which way it's blowing today. There, that's called weather, right? Okay. But also, in addition to these chaotic trajectories and fixed points, there are an infinite number of unstable periodic orbits in the phase space. Now, periodic orbits are just trajectories that close on themselves. And there's the simplest periodic orbit is something that runs around like this. And this is looking at the same thing from different slices in the three-dimensional space. And then there are more complicated. This is one that goes twice around this fixed point, then flips around this one, twice around this one. And there's an infinite number of these. And as you go on, you can classify these by symbol dynamics. You can say, you can talk about the AABBA periodic orbit. That goes around one fixed point 3 times, the other one twice, and then the first fixed point once, and then it repeats the thing over and over again there. And lucky for us, a collaborator, a colleague of mine here at Michigan, Divakar Viswanath, who's a very, very clever fellow, early in the 20th century, 2003, on his own, he wasn't busy one Sunday afternoon, so he computed the first 1,000 unstable periodic orbits of the Lorentz system there. And so these things are cataloged. They're available online for information, for reference. Okay, now, good. So this is a system that's complicated, but we know a lot about it. Let's see how this technology works. Suppose that the quantity that we're interested in, the phi, which is a function of x, y, and z that we're interested in, is one of these monomials. It could be the z variable. What's the long time average of z? What's the long time average of z squared, z cubed? Or we could, or x squared, or xy, or xyz, or xyz squared. We can choose any of those things, depending upon what our particular interest is. It turns out, just for your information, the time average of z is proportional to the time average of xy, and they're proportional to how much heat is transported, or the so-called Nusselt number for the convection problem. Okay, well, it turns out that this semi-definite programming computation approach produces sharp estimates on these things, sharp bounds on these things. And it turns out that each one of these things is maximized on those fixed points of steady convection, which are unstable, turn out to be unstable at these parameter values there. That's where the equilibrium value for z is equal to r minus 1 there. And just as an example, what David was able to abstract, if we want z cubed, and it's supposed to be bounded by r minus 1 cubed, well, equivalently, you can just write this there. And what he was able to do was discover an optimal auxiliary function computationally. This is a fourth order polynomial in 3 variables. You would never guess this. You would never guess it. But this works. Now, if you plug it in, you will find that f phi plus f dot grad v is r minus 1 to the 4th, 27 to the 4th, minus the sum of squares of polynomials. As I say, you would never guess that, but you can check it analytically. So that's the kind of thing that you can extract out of this. And in each of these cases, what one finds is, well, here, the level set, the mountaintop, happens to be a line that passes through those fixed points, those optimal trajectories. Now, this line is not a trajectory, but it says that the optimal trajectories live at that high altitude set, the mountain tops, right there. Okay, now what David also found, and this was kind of a surprise, he thought maybe everything on average is maximized at those fixed points. But when he did z to the 4th, he found that the semi-definite programming was giving him an answer that's bigger than r minus 1 to the 4th, which would be the value at these mountaintops. There, 27 to the 4th. Now, what did he find? Well, there we go. So at the fixed points, 27 to the 4th happens to be 531,441. But what David was finding was, as he used as he optimized auxiliary functions of different polynomial degree, they have to, as you increase the degree you optimize over, you get better lower bounds. At first he got 635,000, 595,000, 592,000, 592,827, 592,827.3. What I've done is I've underlined the number of digits that have converged here. But you'll notice that this is converging to a number that is bigger than 531,441. So what trajectory is doing this? What trajectory is realizing it? Well, if we look at the high altitude set of those are all approximate, nearly optimal auxiliary functions. You look at that high altitude set. Now, this is a mountain range whose base space is 3-dimensional. So I challenge you to envision that in your mind. But I'm telling you, in 3xyz space, the phase space, this red set is the place where that polynomial is maximized. That says that any trajectory that's optimal, and because of the value of m that we chose and our guess for epsilon by looking at the convergence, we suggest is spending 99.97% of its time in that red region, that lovely red region. Well, we can check this now. We go back to Professor Viswanath's catalog of unstable periodic orbits, and indeed we found the shortest periodic orbit, which is unstable, has a z to the fourth time average, which is 592,827.338. And this is where we got with the optimization. How many is that? Six decimals of accuracy. And that trajectory, there it is. It just faded in black. That's that optimal trajectory. So this technique allowed us to discover an optimal, if for some reason, if we were getting paid to maximize z to the fourth on average, this tells us which solution we want to be on. And even though that solution is unstable, then there's this field called control of chaos, which says you can control the system with very, very small expense to stay on that unstable periodic orbit. But that whole field of control of chaos, which you may or may not have heard of, been very popular for the last 30 years or so. That whole field never said how to find the unstable solution that you want to be on. But this method gives you a systematic way of doing it. Okay, so where we are now, this is I'm going to do one more example. This partial summary. Optimal extrema exist. They're accessible practically, and the optimal trajectories can be localized. And you'll notice we did all this no time steps. We never evolved the differential equations. We never spent 750,000 CPUs for 250 million CPU hours to compute anything. We did an optimization with existing packages of semi-definite programming and convex optimization there. Okay, frontiers, of course, going back to my original example at the beginning of the talk, like fluid dynamics, partial differential equations. What do? Here's an example, the Kuramoto-Sivashinsky equation. Now, this is something that you may or may not have heard of. The Kuramoto-Sivashinsky is a one-dimensional, nonlinear partial differential equation for this function u of x and t. So x is one-dimensional, and time is time there. And this equation was derived independently by Kuramoto and Sivashinsky. Kuramoto is sort of an abstract pattern formation, amplitude equation derivation, but Sivashinsky was a combustion engineer, and he derived it as a model of flame front evolution in combustion. And I'll show you what solutions look like. We're going to consider this partial differential equation on the interval going from minus L to L. That's x, goes from minus L to L. And I'm also going to consider, for mathematical convenience, it's going to be periodic on that interval, and odd functions. So functions that are equal 0 at 0 and odd. And what do solutions look like? Here's a chaotic solution for that thing. Now, this is the solution of a partial differential equation, and you see, well, because I pinned it at the center, so that part. But you see, it's kind of unpredictable, and it's supposed to resemble a flame front to you there, and it's got this unpredictability to it, and so when it bounces around and does its thing, and whatever, just like a flame front is kind of chaotic there. Now, I like to think that this is really a model of this guy, but I'm not exactly sure how to model that guy, but I like that picture. Any case, one of the quantities you might be interested in for the solution of this partial differential equation is what I'm going to call the energy density. And when I say energy, I mean sort of the mathematical energy. And that would be if I take my function of x and t, if I square it, u squared, and I integrate it over x, right? So that's sort of the spatial variance of this function. That's a function of time. And that might be a quantity that I'm interested in. Well, it is a quantity that many, many applied mathematicians are interested in. And it's averaged over the length of the interval there. So it's the energy density there. Well, it was conjectured back in the 1980s when people started studying this problem that as the length of the interval increases, that the energy density ought to stay about the same. In other words, as I make the interval increase, It is not the fact that you get very big flame fronts that get bigger and bigger and bigger as you make the interval get wider. And this is a simple thing to state and think about it, but it's been very hard to prove. So it just is saying the same thing, that the mean energy density is order 1 as L. The L is the length of the interval is the bifurcation parameter here. Now, a fellow named Nicholson already, 35 years ago, proved that this conjecture is true for steady solutions or traveling wave solutions, but people want to know if it's true in general. Let me just sort of give you an idea of what these steady states look like. As I said, L, the length of the interval, is the bifurcation parameter. If L is less than or equal to 1, because I think it was 2 pi times L is the length of the interval. If L is less than or equal to 1, then the only solution to the differential equation is 0. And there's a plot of the solution, it's 0. But if I make L a little bit bigger, there's a steady state that bifurcates from it. And these are steady states. As I make L bigger and bigger and bigger, the steady state grows, but then the nonlinearity kicks in, and it actually shrinks again until it gets to be length 4 pi, and then it's just double copy of the original bifurcation. And that hooks up so that if we actually look at a bifurcation structure, that first, the energy density of that steady state I just showed as a function of L going from 1 to 2 looks like this. It goes up and then comes back down. But then there's another bifurcation straight from 2, and it hooks up to that. And that just goes out until you have 4 copies of the sine wave. And that goes out until it goes 8. But then there's another bifurcation at 3. Oh, you can't see my hand when I point to the screen. 3 that hooks up with 6, etc. So you have all these steady solutions of the equations. It's nice to know where they are. But there's also been a lot of work done on this. There's a whole lot of other steady solutions, secondary bifurcations. There's a rich family of steady solutions, and then there's those chaotic solutions in there. And but you'll see with these steady solutions, as the length of the interval gets bigger and bigger and bigger, the energy density doesn't grow. It's bounded by 3 point something there, right? It's an order 1 quantity there. Well, so there's the conjecture. I just said it again. Now, what about rigorous upper bounds? Can we get some upper bounds? Well, it turns out back in the 80s, people were doing this auxiliary function business, but not knowing it. In fact, I was one of the people who started doing it in the 90s and not knowing it there for fluid dynamics. But now, if we look at quadratic auxiliary functions, then, or if we consider those things, then Nikolenko, Scherer, and Tamam. Nikolenko was at Los Alamos, Scherer was in Paris, and Tamam is at Indiana and Paris back 35 years ago. They actually selected an auxiliary functional, and zeta is a function. So this is a quadratic functional of u, and that's a linear functional of u for a given zeta. And they optimized as best they could over this linear, what we call background function zeta, and they were able to prove that the time average energy density is not bigger than L to the 4th. Remember the conjecture is L to the 0. Now, how many years later? 21 years later, Jared Bronsky at Illinois and his student Gamble, I think Tom Gamble was his name, were able to improve the analysis. This is paper and pencil analysis. It's hard analysis. They were able to prove that it's actually by finding a better optimization for that kind of auxiliary function, although they didn't know that's what they were doing. And they were able to prove that the energy density can't be bigger than L squared. Well, what about solving this problem using this semi-definite programming and optimizations? Well, this is the content of the paper that was published in 2019. Again, David Galuskin and his collaborator Giovanni Fantuzzi. Giovanni was a graduate student at the time in aeronautics at Imperial College. Now he's a research scientist there. These guys are both brilliant guys there. And they studied exactly this problem. And what they did was they took the partial differential equation and they did the kind of truncations, the same kind of truncations, these Galerkin truncations that create ordinary differential equations, like for the Lorentz equations from the Navier-Stokes equations. They did this for Kuramoto-Sierpyczynski, and they were able to, and they did higher and higher truncations. Now, what they did, sorry for that extra thing, if they restricted their auxiliary functions to be quadratic functions of those variables, then they produced an upper bound that looks like this. You'll notice that it exactly hugs the stationary solution up to L, just bigger than 2, and then it comes off here. And this is a log-log plot. And interestingly, that's an order L squared growth up there. A straight line on the log-log plot is power law, and it's L squared. And that they discovered that Bronsky and Gamble's analysis, their rigorous analysis, is sharp. It can't be improved because they got an upper bound, which is L squared, which is the optimal upper bound for quadratic auxiliary functions. Well, but we don't have to stay quadratic. We can be more general. We could be that's quadratic auxiliary function. We could be quartic. We could use a different family of auxiliary functions, which are all polynomials in the variables here, and do the optimization. When they did that with quartic, fourth order polynomials, they got better upper bounds all the way out to, wow, and the upper bounds just hugged the steady solutions up until somewhere around, 8, 9, and then it went off a little bit. But now this is starting to suggest something. If you actually zoom in there, and instead of doing fourth order auxiliary functions, you look at sixth order auxiliary functions, and you plug it into your semi-definite program, they found optimal upper bounds that were just sitting right on top of that for as far as they went. So the conjecture here, of course, is that these steady states actually are the solutions of the Skoromoto-Sibishinsky that maximize the energy density. This is information we did not know. I mean, presumably this is true. It's pretty convincing. I say it's a conjecture because we do not have a rigorous proof. I invite you to drop everything you're doing and come up with a rigorous proof of this conjecture because it's almost certainly true. But I've tried and it's not easy. But good luck. Okay, there we are. So optimal extrema exist, extrema are accessible, trajectories can be localized. PDEs is really very much what we want to do these things for. We did Kuramoto-Sibishinsky, and we'd really like to do fluid dynamics. And there's a lot of effort now, both computationally and analytically, to bring this stuff into Navier-Stokes, thinking about turbulence. We want to buy that glass of milk without buying all the cows. And with that, I will stop.
Thank you, Professor Doering, for this great lecture. I would like to us to turn into the Q&A, and so I will be moderator today. So a reminder to use the question icon to ask questions. So it's a moderated format, so once the questions are published, you can see them and upvote. So I encourage you to upvote the questions. And I will do my best to select a broad range of questions. So our first question, and Nisha, maybe we should just...
I have the first question.
Yeah.
Let me ask. Should I leave my screen displaying like this, or should I undisplay? What's the...
I think maybe just we'll go to...
Just leave it?
Yeah, just leave it and maybe go to the format if you need to flip it backwards or something like that.
Okay.
Okay. Yeah. Can we get Nisha? I think maybe we could keep Professor Doering just like the lecture series, and I don't need to be in the camera. Yeah, like that. Thank you. So first question from Andrea Kleiber-Langen. Professor Doering, how difficult would it be to apply your method to a very high dimensional system like electric grid with potentially thousands of variables? And I also want to ask, sort of, you mentioned the PDEs and fluids and so forth, and it's theoretically it's possible, of course, but how practical? I mean, are we getting to...
Right. So for example, to do computations in CFD, in fluid dynamics, to get resolved computations in turbulence, then of course the partial differential equations, in order to put them on a computer, you have to discretize them some way. So you essentially have to convert the partial differential equation into, you have to approximate it by a very high dimensional set of ordinary differential equations, and then basically use the ODE methods on the computer. Well, I will tell you that example I showed at the beginning was many thousands of ordinary differential equations being solved simultaneously, which is why it took the supercomputer. Now, they were doing direct simulations, so then they had to run it for long periods of time and so on in order to get their statistics. For this business, like these example I showed with Kuramoto Subashinsky, David and Giovanni, they approximated the PDE by large sets of ordinary differential equations, and they were using many hundreds for sure. And this was already several years ago. And by now, we know that these semi-definite programs, it's a question of how good are those semi-definite program numerical methods. And these things can handle many variables. I'm not an expert in those things, or actually if David or Giovanni was here, they could tell us what's practical. But I would bet thousands is not out of the question.
Thousands, not yeah. That's very good to know. And of course, there's also the speed up is probably factors of billions, right, or something like that.
Well, besides speed up, the other thing is, if you did a simulation, you'll get an answer, but you don't know if there's another simulation you could have done that would have given you a better answer or a bigger answer for your quantity. So you never really know. But with this thing, you always know you're getting an upper bound, right?
Yeah.
And so it's a rigorous way of giving you the upper bound if you're looking for the optimal, if you're trying to be best on average.
So this is the way to actually find it, even though you can unlikely to see it, right? So so if I may expand on this, my own question, how do you distinguish, or can your method distinguish in, largest on average because everything is sort of bubbling on top, or biggest on average because it has huge spikes, and which is much more dangerous for the operation of the grid?
Right. Well, if you're interested in spikes of some time series, mm-hmm. then you're not interested in the average of the time series. You'd be interested, say, in the average of the square of the time series, or the average of the fourth power of the time series. You want the, Vakhtang, you know what I mean when I say you want the L infinity norm, not an LP norm. Right? So that would be the function that you're interested in is, is determined by what you're interested in. If you're interested in the peak values, then you want to take the average of a quantity that is going to reflect the peak values.
So then you would take u to power 10 or something like that, right?
Correct. And of course, the optimal average of a u to the power 10, if u has average 1, is going to be things that have big spikes in them.
Mm-hmm. So if you want to do the business problem, then you will solve average of u. But if you solve the safety problem, it's u to the 10, right, or something like that.
Right.
And does that pose a particular issue if it's u to the 10?
It depends upon how complex your system is.
Yeah.
I mean, so for example, in the Lorentz equation, David looked at z to the 4th. Actually, not for a physical reason, but we are interested to know. Everybody's familiar with the butterfly wings in Lorentz. If we did z to higher and higher powers, it would be like trying to get, again, the supremum of z. Which trajectory has the maximum value of z, which would be the top of the butterfly wings? And we might want to find that, right? And
Yeah.
you could do it. Is it practical? Well, in principle. And,
Yeah.
and for example, for the Lorentz equations, you could do it. You might even be able to do it for Kuramoto, to at least to get, an indication over a region in parameter space.
Mhm. Thank you. Another question we have from Dan Malak. The semi-definite programming methods are only for polynomial auxiliary functions, correct? Any idea how likely is that the truly optimal auxiliary function is polynomial? Can we minimize the error completely in the polynomial case? So there are three questions.
Right. Yes, that's right. And now there are theorems about this. If you're working in appropriately compact sets in your phase space, and then C1 functions can be approximated as well as much as you like, as closely as you like by polynomials. And in fact, even checking that a polynomial is positive and checking that it's written as sum of squares, because there's that little gap in there between is it positive or is it just sum of squares, right? Which is a subset. That gap goes away as well. Then, in other words, if you take the degree of the polynomial high enough, then you can approach the true optimal as closely as you want. In other words, you can approach the true optimal even if it's not polynomial. And we have lots of examples where the optimal is not truly polynomial, but you can get the answer as closely as you like by polynomial approximations.
Mhm.
There. And also now for other dynamical systems which are not polynomial, for example, a dynamical system where it's periodically forced, so it's non-autonomous. It has sine omega t. You know what non-autonomous forced systems are, like the forced pendulum kind of problem, periodically forced pendulum. Well, those we can actually turn into autonomous dynamical systems. We can even turn them into autonomous polynomial dynamical systems. And then then it's a matter of being clever and seeing how can you convert non-polynomial dynamical systems into, how can you either approximate them or rewrite them, usually by introducing new variables, as polynomial systems. And so far, we haven't been obstructed for any case that we've been interested in so far. There are probably counterexamples, but we're applied mathematicians, so instead of looking for counterexamples, we look for things that work, not for things that don't work.
Yes, very much agreed. Thank you. The next question is sort of on a lighter side. Thank you for your presentation. Not related to the presentation, but I'd like to ask about the button on your sweater. Can you tell us about it? Thanks.
Yes. This is it's a button that what it says, the writing, it says, "Ain't no time to hate," and that is just below what's called a "steal your face" symbol from the Grateful Dead, and inside that is the flag, the LGBTQ colors, and this is something, a pin that goes back to the 1980s, for those of you who are Grateful Dead fans, where they were just saying, hey, words to live by, ain't no time to hate, let's do the right thing.
Thank you. Another question is about, is this, given the relationship between some stochastic differential equations and PDEs, could there be applications to financial mathematics such as portfolio optimization?
Yes.
So I can give you,
yes.
I can give you all my money, and you guarantee I will win with you.
Well, because already the PDEs, the stochastic differential equations relationship with PDEs, those are like Kolmogorov equations, or Fokker-Planck equations, right? And those are equations either for expectations or probability distributions, right? So I can optimize probabilities, just like your financial analyst says. I can give you the best average advice, right? So,
all right.
but of course, yeah. I mean, the underlying stochastic process is stochastic. So, of course, if I knew what the market was going to do, then I could tell you what the optimal strategy is, right? For each trajectory of the market. But we don't know that. So there's this inherent stochasticity in there. But we can certainly optimize probabilities or expectations. In fact, what I've just done is I've optimized expectation of a function. These were for deterministic systems, but that could have been a stochastic system. In fact, and there's papers on using these techniques for stochastic systems as well. It flows right over. There are invariant measures. If there are invariant distributions, these are long-time averages, right, for the expectation.
And we have a comment from Dan Malak, who asked about semi-definite programming methods. He says, that is a fantastic answer. Thank you, Professor. So I think this is, as far as I can see, there are no more questions. We have, and our time is pretty much up. Thank you, Professor Doering, on behalf of ATCO, the transformation team, and all the listeners. We love to have you here, and we hope to keep our connection with you in the future. And thank you again for your insightful talk.
Thank you very much, and I hope to come and visit you sometime in the summer